Okay, it's 8:30 UK time, so we need to start. So welcome. My name is Laurent, or Laurent, or any variation thereof will do. I live in Cambridge, and I teach and do research at the university there, but originally I'm a French speaker. So we are here today to learn about statistics and to learn to use a programming statistical environment and programming language called R. And that's what we're going to focus on for 2.5 days. But before we get into that piece of technology, I would like to get started with this other piece of technology that is extremely important for teaching, and this technology is called sticky notes. And so one really important aspect when teaching, when going to a course, is interaction, right? If I teach, I try to kind of share some skills and content with you. It would be very difficult for me to know whether I do a terrible job or I do a good job if you don't interact with me. And similarly, for you to get most out of it, you are welcome. I encourage you to ask questions and stop me anytime, right? And so these sticky notes are meant to help us to improve interaction between ourselves. So feel free anytime to raise your hand, to call me, ask me to come, or ask any of the TAs. There are, I think, 4 TAs scattered around the room amongst you. They are here and hidden, but they watch and they are here to help. And I'll be also helping you and come to help you. Right, so you can raise your hand and we'll stop and we'll make sure that everybody is comfortable and understands what we will be doing. But coming from Britain, having lived long enough in Britain, I know that some people are not comfortable with raising their hands, attracting attention, and ask a question. So we are also going to use these sticky notes to convey 2 types of information. So we have 2 colors. This color that I will at times call red, pink, orange, conveys information. There is a problem, I have a question, something is not clear. This other color, that obviously is blue, but I'll surely also sometimes call green, and I apologize in advance, conveys information, I'm happy, I'm okay, I understood, we can move on. So if at some point during, not the lecturing, because it won't be a lecture, during the discussions, the interactions, there is a question, and you don't think it's the right time to raise your hand, feel free to use this color and paste it like this on your screen. So I'll see it, I'll be looking for sticky notes. And so I know that that's either immediately, or maybe I'll finish my sentence, or maybe even go on with another sentence, but I know that very quickly I'll have to stop and ask for a question, or clarify something I've said. Okay, so I'm going to give you these 2 packs of sticky notes. Could you please help yourself? Take one of each color and then pass it to your neighbor. We will also be using the sticky notes when we do exercises. So I'll describe a task to be done, and then you'll do the task. And as soon as you are happy with the task, whether you have finished the task or you think it's fine, we can proceed, I don't mind, reading my email, or as soon as you are happy that you understood what was had to be done and or you did it, take the green, again, I'm already mixed up with the blue sticky note, put it on your laptop screen. Okay. On the contrary, if there is a problem, take your red sticky note, put it on the screen, and any of us, TAs or myself, if we see a sticky note, will quickly run towards you to help. Okay. Sticky notes technology doesn't fail, as opposed to computers. Okay. Another really important role of these sticky notes is that while you do the exercise, I'll be able to see what kind of progress you make. Okay? If I don't see any sticky notes, clearly you will need more time. If I see a majority of blue sticky notes, I know that we can finish, the exercise time, and we can look through the solutions together. If I see red sticky notes, I know that, there is a problem. Good. And I invite you to ask as many questions as possible. So, is there a question so far? Good. Have you been made aware of this Piazza webpage for the Media Institute? Let's try the sticky notes out. Does everybody have a sticky note? Those that do not have a sticky note, please put the red sticky note up. Okay. Good. So if you are aware of this page, please put your blue sticky note up. And I don't see blue sticky notes at the back, which probably means you haven't got the sticky notes yet. So on this course landing page, here there is a link that says Google Drive May Institute Presentations. If you open that link, you'll be graded by these 7 program folders. We are program 3, and I'll ask you to download this file called intro-rfiles.zip and download it on your computer. Okay? So sticky notes down, please. Could you download that file? Once the file is on your computer, put your blue sticky note back up, and if there is a problem, use the red sticky note. I generally try to gather a little sweetie, a little piece of chocolate or a sticker. As you can see, I'm a great fan of stickers. But somehow today I forgot to bring it. And that present is for the person that asks the first question. But I was a bit in a rush, so I failed. I'll try to get something, and then tomorrow morning, first question, we'll get a little bit. Right, good. Enough about this. You see, we would already struggle without the sticky notes. Anyway, can you take the sticky notes down, please? And so the second exercise will be to open our studio. I assume everybody has downloaded and installed our studio. If so, could you start it? And something similar like that should pop up on your screen. Once you have our studio open, blue sticky note up. By the way, a quiet classroom, in the real classrooms where people work, it's fine to have a constant noise, not too loud, of course, so that people that want to listen to me can hear me, but it's fine for there to be activity and questions to me, but talking to your neighbor. So if you have a question, you're not sure about something during an exercise, help each other. That's a really good way. Peer instruction is a really, really good way for you to learn something, but also by explaining it to your neighbor. It's one of the best learning techniques that we know of. And so I see a majority of blue sticky notes. So I assume that our studio is open. Okay, so I'm going to do a couple of changes here that you don't need to do. The first thing I'm going to do is that I'm going to increase the font. Is this font large enough? People at the back, can you read here?
Yes.
Good, thank you. Right. And I'll do some additional changes, but I'll do these later on. Right. There are no slides. There is material that is ready, but that I'm generally not going to show. All the material is available at this URL. Okay, so if you browse there, all the material, everything I'm going to say, and much more is available. Okay? But I don't want us to feel obliged to follow the material the way it is kind of written up. We have the freedom to move from one thing to the other depending on your interests and the immediate needs. Okay? Good. So, who knows about R? Is there anyone else? Is there anyone in this room that already knows about R and has already used R? Yeah, okay. Okay, that's very good. I think some TAs have shown their hand. That's good. That's reassuring. I have raised my hand, so that's reassuring too. But other people, very good, that have used R. So anyone, non-TA, could maybe give me a reason, or why they have used R, why they think it's good environment, or why it's very annoying, or why they don't like it. Is there a volunteer? No? Okay. Pardon?
Table generation.
Table generation. Graphs, yes, that's true. That's one of the things that R is well known for, graphics. Okay. Anything else? Yes?
So far in Excel.
So a little bit louder.
We can only go so far in Excel.
Yes, only so far. So what can't you do in Excel that you expect to be able to do in R?
Handling of like large data sets.
Okay. So what is a large data set, for example?
Thousands. Like you could have like a table, for example, it's like thousands of rows, thousands of columns.
Okay. So a table with thousands of rows, thousands of columns. I'm not an expert in Excel, but I think Excel should be able to handle such a table. I think it should be able to open it. Okay, but actually, thousands of rows, I'm sure. Maybe not thousands of columns. But actually, even if you were able to open that large file, that would probably not solve your problem, because the file would be so big. What would you do? How would you kind of scroll left, right, up, down? Right. I don't know, but again, I'm not an expert in Excel. However, at some point when the data becomes large, you need to learn different techniques to kind of attack your data, to master your data, to be able to look at it. Even though looking at your data is not looking at cells, looking at the values in the cells, you need to learn some techniques to manipulate that data, to gain some understanding of that data, to understand it, right? And this is something R is really good at. Not only because it will handle big data, or many different types of data, different types of formats, but it comes built in with plotting capabilities and other data manipulation functionalities that will allow you to get a handle of R. Okay? And these features that come with R, these functions, these capabilities, come through a command line interface. Right? So it's not about using the mouse. You'll have to type in these commands to tell R what to do, and then it will return the result. Now, not using the mouse can come as a little bit of an inconvenience. I appreciate that, but it also comes with many, many advantages. One advantage is that by writing your commands, your instructions to R, you will be able to repeat every step that you have done later on, with the same data set, with a different data set, with an updated data set. Okay? And even better, somebody else will be able to do the same thing with the same data set or with their own data set. So it will allow you to repeat the analysis, including your future self. And my future self, or myself, doesn't always understand what my past self did. And so being able to read exactly what I did as instructions of R code is extremely helpful. Okay, so R, or writing code, whether it's R or any other programming language, will allow you to work reproducibly. So we are here in a kind of a proteomics workshop. And so I assume that you are all familiar with proteomics or some sort of omics, no? What do you work on? Biostats, okay. But so R is by nature multidisciplinary. So it's a statistics environment that allows you to do statistics, to do plotting, but R has a very interesting extension mechanism called packages. And by loading these packages, downloading, installing, and loading these packages, suddenly R knows much more than the basic statistics that come built in with R. All the basic plotting capabilities that come with R. Suddenly, R becomes a tool that can be used for high-throughput sequencing data analysis, proteomics, ecology, and so on and so forth. R is used across many different fields, in academia, but also in industry. And another, I think, really nice aspect is that R is an open source software. And that means that, well, you don't pay for it. But that also means that many people look at its code. And so many people scrutinize the code. Many people can contribute to the code or to the code base of R through packages. So there is a large community of people behind R. And that's very important, maybe not for the kind of intricate codes, low-level, very complicated code that comes with R. But that's really important from your perspective if you want to use R to analyze, say, proteomics data, or any kind of biological data. Chances are that at some point you will have a question when you analyze your data. And that question might involve some stats, that question might involve some programming, that question might involve some biology. And there are places online, support forums, where you have this multidisciplinary community that will be there to answer your questions. And we will see later on how to find help, how to find this information about R. Now, R is great, but what we are going to use is not R directly, but we are going to use another piece of software that is used as a front end to R, which is called RStudio. Okay? And here what we see here is RStudio. Does your RStudio look like this? Do you all have RStudio up and running? Okay. So here on the left-hand side, this is actually R. Okay? The piece of software that is shown here is R. Here we have the greater than sign and the prompt. So this here means that R is waiting for us to provide some instructions for things to do. Right. But RStudio comes with additional panes here, and I'm going to open another one here by clicking on this button here, and then click on R script. Okay, create new R script. I'm going to increase the size. So here I have these kind of typical 4 parts, 4 panes of RStudio. The actual RStudio command console. The one here top left is an editor. That's where I can write scripts and save my scripts with my R instructions. And on the top right-hand side, I will see a list of everything that I have created so far in R. So currently there is nothing. Later on we'll see how to populate this. And here's another one where, for example, our plots will show up. And it's also one where we'll be able to navigate the files. And that's something we're going to do in a minute. All right? So I'm going to do an immediate change in my RStudio configuration. I'm going to move this one at the top, so that I have my script and my console next to each other at the top. And the reason I do this is that these are the two most important parts of RStudio, and I want them to be at the top so you can see them. Okay? You might struggle to read what's here at the bottom if I'm standing here. Okay? So feel free to change this if you want, but you don't need to. Okay, still the same panes, but in a different configuration. So, next thing we are going to do is to create an R project using RStudio. You might not believe me yet, but writing code is something that is pretty easy to do. Generating figures in R is something that is pretty easy to do. And by the end of tomorrow, you will have written a couple of R scripts. You will have generated a couple of files. And suddenly you might end up with a directory with files and figures, and not really remember what is what. Maybe you take different courses. So a really important aspect when doing, let's call it statistical data analysis, or running a computational project in general, is to start with some sort of idea where the files will live. You know, input files, output files, figures, code files. And of course there is no single rule to do that. But I'll give you a suggestion how to do this using RStudio. And so the first thing that we are going to do is to create an R project. To do this, we click on File, and then New Project. Okay. And then in New Project, so we want to create a project, and we first need to say, where are we going to store this project? And I would like to do this in a new directory. So I click on New Directory. Feel free to do it whilst I do it. If not, I'll give you a couple of minutes later on. So there are all sorts of types of projects that can be done using R and RStudio. Here I'll click on New Project. I don't want to create an R package or a Shiny app or so on. Okay. So the first thing I'll need to do is to provide a directory name for this new project, where my project and all the files will be stored. And I'm going to call it R intro, or maybe R intro 1. And maybe tomorrow I'll want to create an R intro 2 and so on. And now it also asks me where I want to create this this new project. And I'll just leave this to the default. I assume my config is, well, yeah, I assume this is a tilde that says store it in my home directory, which probably on this computer is the kind of my documents directory. Okay. But feel free, if you have already a directory for this May Institute course, to browse and navigate there. And once you have done this, create project. RStudio is going to restart into the new project. So I'll wait here until you have created the project. Blue sticky notes up if you have, red sticky notes up otherwise. And I apologize in advance. I will probably get very, very annoying towards the end of the course, reminding you with sticky notes, blue, red, and so on. But and of course, if you are annoyed with the sticky notes, but it's a really good tool to see how we're doing. Good. So normally here in this file browser, you have rintro1.rproj, or whatever you called your project, .rproj. So this is the directory on your hard drive, on your disk, where this R project lives. Okay. So what I'm going to do is that I'm going to create a first directory that I will call data. So this directory is where I will want to have all my input data stored. And we'll see later why this is important. I will maybe also create a new directory called figures. And that's a directory where I'll store all the figures that are produced. Yes?
Can you save this as like a template so all of your folders are within a...
That's a good question. So for example, if you want to say, create a new project or type of project, and that would be your specific type of template with these files and these directories. I'm not sure. And I'll make a note and I'll have a quick look. Thanks, but that's a very good question. Yes. Does anyone know? Maybe. Yeah, that's a good point. That's a workaround. So what you could do is to create it, start with it, create all the files and directories, and then copy it over and over again. Yeah. But I'm pretty sure there is a way to specify it somewhere. And if not, it's probably a nice feature request for RStudio. Right, so what other directories will we want? So for now, I think these two directories are enough for us. But we could also have a kind of data output directory. Right? This now, the convention is, this is input, files that contain some sort of data. In our case, this will mainly be kind of spreadsheet type files. But we will also create new data files. And so we could have a data output directory. Okay. We could also have a source code directory. In this case, we will create the source code files that have a .r extension in this project directory. But if for whatever reason you think it's better for you or for your project to have one or multiple source directories, this will depend really what you need. But this is a good starting point. Okay. So the next exercise I would like you to do is to unzip that intro R files.zip file that we downloaded a couple of minutes ago, and then take all the files in there and put them in this data directory. So could you take all your sticky notes down and put them back up once you have all the files ready into that directory. Okay? And I'm going to do the same thing here on this computer. Okay, let's continue. But I think there was a very good question there. Could you ask it?
Yeah. How can you say the working directory and change the name of the folder to be changed with insert?
So the question was about the working directory. How do you know about the working directory?
So we save the working directory.
Okay, oh, I see. So it did mention working directory on the track. Okay. So working directory is actually a very important concept when we work with R. If we ask R, we will be asking R to open a file, and we will be asking R to save files or save figures. Where is it going to look for them if we want to load a file, or where is it going to store the figures, the files, when we ask R to save the files? In the working directory. Okay? And so in my case, my working directory is in my home folder, which is my documents, R intro 1. This is the working directory of my project on this computer. Okay? And it's very likely that, well, actually, it's sure that we all have different working directories. Okay? Because we have different usernames, so we will all have different working directories. So if I ask R to open a file called, spreadsheet.csv, it expects to find the file in the working directory. If my file spreadsheet.csv is in my data directory, and that's where I, from now on, expect my input files to live in, then I'll have to specify to R load or read file spreadsheet.csv in data. So I'll have to say data/spreadsheet.csv. Okay, so working directory is the location on disk where R expects to find things. And if the files are not in my working directory, I'll have to specify the full path to the file. All the succession of directories and the file. Okay. So I'm going to press Control L. Control L clears my console. Okay? And I'm going to do that regularly so that whenever I start to type something, it shows up at the top and you can see it. Question? Yep. Control L for clear screen, obviously. Yeah, and there will be a couple of keyboard shortcuts that are completely counterintuitive, but that are good to learn. So I know Control L because I like for my screen to be kind of clear and start at the top. It's like I have a fresh mind and then I can tackle my computer issues. Right, but let's focus now on the console, which is really R waiting for us. And so we can use R like a giant calculator, where I could, for example, ask it to do this. Right, this is not R, this is the computer, and I will ask. Yeah, that's good. Great. You see sticky notes, that will not happen with sticky notes. Anyway, so I was saying we can use R like a giant calculator, 25 plus 162, and I trust R to give me the right answer. Right. And I can keep on trying it out like that, and it will work. And assuming that 1.71 and so on is a really important answer to what analysis I do, I have my answer, but it's kind of lost. It's printed on the screen. So we need a way to save the feedback, the answers that we get from R. And how can we do this? We can do this by creating little containers that will store values. Now the technical term is a variable. The variable is a little container, and these little containers need to be named, right? So I'm going to create a little container variable called x. And I'm going to assign a value to x, put a value inside my little container, and let's say I'm going to say x gets value 1. So how am I doing this? Oh, I type x, and then 0 or multiple spaces, and then an arrow pointing towards the x. And the arrow is a smaller than sign minus. And then 0 or multiple spaces, and then the value that I want to store inside this variable. Okay, enter. If you see here on the left, this part was empty, and now I see x that has appeared. And next to x, 1, which is its value. To avoid any confusion, or maybe to confuse you even more, I'm going to create another variable another variable that now I called y, and I'm going to assign it value 2. As you can see, y appears here with value 2. Right. Now, for x, I used the kind of arrow operator, and for y, I used an equal. Both are equivalent. It doesn't matter which one you use, but some people will have big fights on mailing lists saying that one is better than the other. Obviously, I have my opinion, but that is completely irrelevant. If you prefer to use an equal sign, use an equal sign. If you prefer to use the arrow, use the left arrow. And if you want, you can learn a new keyboard shortcut, which is Alt minus. Alt minus will automatically create this left arrow assignment. So here we have created two variables, x and y, and we have assigned values 1 and 2. And they also appear here. Now what happens if I type y times 2? And if I click enter, but before clicking enter, I would like a volunteer to tell me, oh actually wait, not yet. First, if I type y and enter, the output is 2. Okay? This means, dear R, give me the value that is stored inside variable y. Okay? If I type x, it means, dear R, give me the value that is stored inside variable x. And if I type z or z, and I press enter, R is going to tell me to sod off because there is no object z. Object or variable, different terms that essentially mean the same thing. Okay? And indeed, there is no variable z listed here in this global environment. Right? So let's try to understand let's define what global environment means. The global environment is a little bit like the working directory for R, where it expects to find things. But these things are not files. These things are the variables that have been created so far. Okay? So, global environment is where R expects to find the variables. The working directory is where R expects to find files. The files survive, restarting R. All the variables will disappear if we stop R and start it again. That's kind of a working memory of R. And if I ask for variable z, it will try to find it, and then it will complain if it doesn't find it. Back to my question, what happens now if and I'm going to make this smaller. What happens if I type y times 2, that's the asterisk, and press enter? Does anyone want to adventure? I'm guessing the answer that I will get? 4. Yes. Let's check. Yes. So what's happening when I say y times 2? R is going to look at it and say, okay, this is a multiplication. I know about that. That is 2. Okay, no problem. But here on the left-hand side, we have y. What is y? Well, R will look into its global environment. It will find a variable y and replace y by its content. And then multiply 2 by 2 and return 4. Same thing if we do it the other way around. Yes? Yes. Right. This is something we'll see later. But I still want to show you this because otherwise my explanation of number 1 won't make sense. This is the index of the answer. Here the answer is only one single value. That's why we see that once, but they don't make much sense. The answer to this instruction is the sequence of values from 1 to 100. This is the first item in my sequence. That's the 12, the 13. So it means that anywhere in my sequence of numbers, this one is its index, 67, 78. Let me give you another example. Oh yes, and I will. Letters. A is the first letter, L is the 12th letter, W is the 23rd letter. So these are kind of the indices of the output. We'll see this later on a little bit more formally. Okay. Next thing, let's create a script. Let's repeat what I did before with file, new file, file, new file, R script, or we could press Control-Shift-N, or we can press this little button here, and then R script. This opens this pane here, and yes? Control-Shift-N. N, like, N. Pardon? New. Thank you. Yes. And then I'm going to save that file immediately by pressing Control-S, and I'm going to call it script.r. Generally, we would use the extension R, capital R, or lowercase r to save our source code. Other accepted file extensions are S. And the reason for that is that before R, R's predecessor was called S, for statistics. And I think in the official manuals, they even say that the letter Q is accepted. I have no idea why, and I have never seen it in real life, but I would be really interested if anyone could point me to such a file. Don't create that file in your computer and call me. Okay? But I have never seen it. It's a bit weird. Anyway. So, save, and what happens? I have now this new script.r file in my working directory. By the way, why do you think that R is called R? Anyone? Well, S, R, they're next to each other. But also because the two people that started R, their first names start with R. There is Rossi Harkar and Robert Gentleman. And actually, Robert Gentleman is also the person that started Bioconductor. Who has heard of Bioconductor? Oh, many people, good. Bioconductor is kind of a project that provides a set of R packages, these extensions, that are dedicated to the analysis and comprehension of high throughput. Officially, it says high throughput genome. Sorry, yeah. It somehow says genome, but I don't like that. I prefer to say high throughput biology because it's not just genomics, it's proteomics, mass cytometry, and so on. So these are kind of packages that are specialized to analyze biological data. And so Robert Gentleman also started the Bioconductor project. And apparently R is from there, their first names, and then because they designed R as a successor of S. Not because F was not good, but it was a commercial piece of software, and they wanted something that they could use for teaching without having to pay for this expensive software. Yes, now I've lost, yeah, script.r, here we are. So, what I've done so far is to type my commands immediately here in my R console. And somehow they are lost. Now they are not completely lost because somewhere here I can click on history and let me resize this. And here are all the commands that I typed. Okay, so here's my whole history. But it's not quite good enough. Oh, and actually, if I'm in my R console, here I can use the up arrow to go back in history. Okay, you see? Up and down. That saves me some typing. And we'll see a couple of additional tricks later on to save typing. But yeah, even though my commands are available here in the history, that's not a good record of what has been done. A better way to work reproducibly, to store what we do, is to write our instructions to R inside this script. So for example, let me create a variable A and store 10. So this is something I write in my script file, and I'm going to immediately save it, Control S, because this is an important piece of data analysis that I don't want to lose. And now I'm not going to lose it, even if my battery is empty, because it's saved in a file. My hard disk can crash, but that's not a problem because I have regular backups. Right, so I have written this instruction in this script, but as we can see here, there is no variable A. So it's in the script, it has not been executed by R yet. So how can I do to execute it? To make R execute that command. I could copy and paste, but that would not be very convenient. What I can do is to press this little button here, run. If I try this little button, run, then the line at which my cursor is will be automatically executed in R. Let's try this. Here we go. Okay, I press the run, and automatically A gets 10, is executed, and A appears in here. Another way would be, let me now overwrite. That's also a new concept. If now I write A gets assigned 11, let me click run again. So click run. A gets 11. Variable A already existed. It was already here, but now its content is replaced. Third attempt, A is 12. Now instead of using my mouse and clicking on the run button, I'm going to press Control Enter. Control Enter is a keyboard shortcut to run here. And Control S to save my script. So I'll try as much as possible. Maybe when I wildly try some crazy ideas that I know are not really important, or maybe create temporary variables, I'll do it here. But whenever I want to write something that is important and that needs to be recorded, I will write it in my R script and then execute whatever I need to run with Control Enter. I could also, is it this button? Oops. Yeah, I could also press this button, which essentially means execute everything that is stored in this script file. I could also select a region of my file of interest, press run or control enter, and it's going to rerun these lines that are executed. And we'll see later on that this is very handy when we, for example, build graphics and we try things and they look good but not as good as we want them to be. We can update our script and kind of re-execute the same piece of code until we get exactly what we want. Okay. Something else we haven't seen yet is how to add commands in a script. So I can write any arbitrary text in a script file that will be ignored by R if I prefix with this dash. If I try to execute this, control enter, you see, nothing happens. R just carries on, knows that this one should be ignored, and starts to execute my next command. I could also comment a line of code, and if I re-execute this script, this line of code will not be executed. Okay. Maybe commands seem futile at this stage, but believe me, documenting your scripts is extremely important. It is really important. In the moment, everything is probably clear, but once you start to do a little bit more complex data analysis, and you get scripts that are 10 or 100 of lines long, having comments, maybe just that comments that separate your long script into sections. You could have different scripts if you wanted, but in writing comments will be very, very useful to kind of structure your script, but also structure your thoughts. How to do the analysis, why you do one thing and not the other. Okay. Any questions so far? So we have seen the working directory, we have seen the global environment, we have seen our projects, we have seen the console scripts, and we have seen how we can create and override variables. The next thing we are going to see are functions. So how do you know that what you see on screen is a function? You know it's a function because it has a parenthesis. So when you see round 3.14, it's a function because you see in parentheses. Okay? So control enter, here it is. So a function is like in maths. It's this entity that takes an input, does some work on that input, and then returns an output. The input always comes inside the parentheses, and the output is what is returned and that is printed here. And the name of the function is this point, okay, just before the opening parentheses. Round is a function. Let's try to do the following thing. Be sqrt for square root of a. So this instruction becomes actually, you know what? Let's be a little bit wild here and type this. And this is a big step compared to what we have done so far. In this one line of code, we have a function, we have an operation, and we have an assignment. And this might look a little bit convoluted, or it might not, depending on your experience, how comfortable you are with reading source code. But I think Most difficult thing when you are new to programming or data analysis is to familiarize yourself with the syntax. It's a little bit when you learn a new language, of course you need to learn the words, but really you also need to learn the sounds. You know, you need to familiarize yourself when there is this new word coming. Does it hurt your ear? What does it sound like? Something that you can process. It's the same thing with programming languages. You can see this as utter gibberish, a random succession of characters and spaces. And it's normal if it looks like gibberish at this stage. But hopefully by the end of today, and certainly tomorrow, this will start to make sense. When you look at it, it will immediately make sense because you will be able to process it, to look for important signs, important characters that will help you to decode this. Let me give you another example. When my children start to read, it's not exactly like that I started. I learned to read. But when they learned to read, they first got very short words, like cat. And they were taught to start to take that word cat and cut it into pieces. These pieces are letters. So they saw C, A, T, and they were also taught to the phonemes associated with these letters. Like C would be K, the A would be A, and the T would be T. So they have CAT, they have to split it into C, A, and T, match the signs they see with the sounds, put the sounds together, and say cat. Of course, if they have bigger words, they had to split the bigger words into phonemes, the sounds, figure out what sounds these represented, put them together, and say the longer word. I hadn't realized, before my children started to read, that it's exactly the same thing when you learn a new programming language. So this gibberish, you need to identify the bits of the gibberish that are kind of single pieces of information. Like, for example, if we take SQRT, just QR does not make any sense. So focusing on QR, we just increase the level of confusion. We need to identify the characters that help us to split this kind of expression. So we know we have just learned about functions. So if you see a parenthesis, this is kind of an anchor point. I see a parenthesis here. So I know that what is left of the parentheses is the name of the function. And I know that everything that is between the opening and closing parentheses, or bracket, how do you call these? Parentheses, okay. Everything that is within the parentheses is the input of the function. And the input of the function can be a number, but the input of the function can be something bigger and more complex, an expression of its own. And that's what we have here. It's an expression, an operation, a plus x. And now that we know about variables, we shouldn't be confused by a plus x. A is a variable that actually contains 10. X is a variable that contains 1. But we don't need to know that. We don't need to know that a contains 10 and x 1. R will figure it out for us. We don't need to make this manual calculation that actually what we are going to do is to calculate the square root of 11. R is going to do that for us. We need to be able to see this operation and see that here I have a function A and here I have the input of that function. And that input of the function itself is an operation, in this case an addition. Another important symbol to look for is the assignment operator. So I know that at the right-hand side of the assignment operator, I have 1 line, 2 lines, 10 lines. Here, something will happen and the value will appear. In this case, the value is the output of that function, and that output will be assigned to variable b. Does variable b exist? No, it does not. then I will create a new variable, b, and store the output of this, whatever it is. It's not for us to calculate the output. This output will be stored in b. If the variable already exists, then the content of that variable will be overwritten. Let's run it, and here we are. B now contains 3.3166 and so on. So functions. Look for parentheses. If you find parentheses, you know that what's immediately in front of the parentheses is the name of the function. Now, if you're not quite sure what that function does, but you know its name, what you can do is to go here in the help, where am I? Here, in the help pane, and search for sqrt. Or, if you don't want to click on help and want to keep, and you are in your R console, you can also type question mark sqrt, or question mark and the name of any function, and this will fire up the documentation page of that function. And in every function in R comes with a documentation page. So let's look a little bit at this documentation page. So all the documentation page have the same structure. They start with a title. Here we have the name of the package where it comes from, and generally here we have the name of the function, but in this case it's more a general documentation page that documents two functions, square root and absolute value, so here it's kind of mathematics. But we have a title, and then a short description of the documentation page, a usage, which tells us how to use the function, the name of the arguments. Arguments is a fancy word for inputs. Some details, references, see also an example. And these documentation files are very, very useful. They are very accurate. They describe things exactly how they should be in a very accurate and technical way. So all this is good. The downside is, unfortunately, the first time you read the documentation file, it's very likely that you won't understand what they try to convey. And I say you, but I should say that. Whenever there is a new function, and I look at this documentation page, I struggle to really understand what the function does and what the documentation page tries to explain. And that's because these documentation pages often tend to be technically accurate, very correct. But then, fortunately, there is the examples here at the very bottom. And so typically, my advice to you is, when you open a documentation page, let's try to open maybe another one here, a question mark, round, oops, here we go. What I often do, I read the title, rounding numbers. In this case, it's not too bad. I have a quick look at the description, but I want to learn about round, and the first word of the description is ceiling. That's not a very good start, unless you know already what round means, and you know what the ceiling and the floor of a number is, then it's fine, but if you don't know, then this is not very helpful. Okay, anyway, and so very often what I do is that I navigate to the very bottom of that page and start to run the examples. Okay, to try to get an intuitive understanding of what the function does. I try it out, and then once I start to understand, I go back and read the description again, and maybe the technical details. That's just the way it is. But whenever, when you have questions, course, here in the classroom, raise your hand, use sticky notes, and ask us all the questions you want. When you're on your own, look at the documentation files. Otherwise, there are also kind of online forums and mailing lists. There is an R mailing list, an R help mailing list. There is Stack Overflow, there is a web page for programming questions, and there is a specific R tag where you can ask questions about R. So there are many kind of places where you can ask for help. But just as we have examples here in this documentation file that will help us understand what the function does, whenever you have questions, maybe the mailing list, in the forum, and so on, try also to provide little code examples that describe your problem, that describe your errors. That will help people to understand the question, reproduce the error, and then help you with an answer. Oh, but let's look a little bit more here at the documentation of round. And in particular here in the usage section and the round function. And there are different functions that are related, which are ceiling, floor, trunk, and signif. And actually, another interesting section here is the see also section. There is another function called as.integer, which is somehow related to the round function. And so documentation page are also an interesting way to navigate through the different functions that you have in R. But let's come back to the usage section here. And so if we look at round, we find our function name, opening and closing parentheses. And the other thing we see inside round here is a little comma, and something on the left of this comma, and something on the right. And these are two different inputs. The x input is a number, a numeric factor. We'll get back to that later on, a number. And then the second one, called digits, is an integer, a number indicating the number of decimal places or significant digits or significant digits. So let's try to use it. Here, I'm going to type round. Okay. So if I execute round like this, it returns 2. It returns 2 because the default value for digits is 0. So the default behavior of round is to return 0 significant digits. If here I now change this to digits equals 2, it will return 2.38 because I now explicitly said I want 2 significant digits. I could also, and let me keep everything that I typed. I will struggle with this keyboard. Like this. Let me execute it like this. Control Enter. Exactly the same result. So whether I say digits equals 2 or just 2, that's the same effect. Because there are two ways to provide inputs or arguments to a function. I can explicitly name my inputs, like I did here, digits equals 2. Then it's a matching by name. Or the matching can also happen by position. So if I write 2.38 and so on, comma 2, R will automatically figure out that 2.38 and so on needs to be mapped to X, which is the number that I want to round. And the second one, too, is automatically mapped to my second argument, that is digits. And so most of the times when using R, when calling functions, we'll probably write it like this, without explicitly naming the arguments. If we have more arguments to a function, 3, 4, 5, and so on, we will probably start to name them because it becomes more difficult to remember the position of all the arguments. But most of the time, we never name the first argument, rarely name the second argument, but as soon as we use more arguments, more inputs to the function, we'll start to name them. What we could also do is to write something like this. That would, of course, be very, or even, would, of course, be very confusing, but this would work. Okay. Here we map by name, and here by position. Because this one has already been mapped, this one will be automatically used as X. I'm showing this as an illustration. Please do not do this in real life where you start to swap positions. This will be very confusing. But it shows you how the matching works. Okay? Any questions so far? Okay, so I would like to have an exercise for you. And so if we look into our files here, into the data directory, there is a file called iprg.rda. So I would like you to load this file rprg.rda that lives in the data directory. Load it with a function called load, and store the result into a variable called x. Let's call it x. Okay. I will give you one important piece of information, is that the input, so the name of the file to the function load, will have to be quoted. Okay. Like this. It will need to be quoted like this. Okay. So the function is called load. If you need more information, question mark load, and you'll have the information. The file is called, let me type it here, and I will write this as a command. Oops. So this is the name of the file. Let me. The file lives in a directory and new variable if you haven't any variable x, or a variable x. So could you load file iprg.rda? That file lives in your data directory. Now, if we all have created a project, an R project, and created this data directory in the project, these two pieces of information should be enough to indicate where to find the file. Do this with the function load, and store this result into a variable x. Okay. Could you try to do this? And either use a blue or red sticky note. Oh, and the last piece of crucial information is that don't forget to quote the file name or the full path to the file name. Yes. Sorry. Please forget this piece of information. Oops. Function load. It's clearly already very late for me. Forget about assigning a variable x. And if you have done it, it's fine. But what you need to know is function load and load IPRG RDA file into the data directory. Let me show this. So we have the function load. It's a function, so I use parentheses. And then I need to start with data. That's the directory where my file lives. So I can press DA and then use the tab key for tab completion. And RStudio is automatically going to detect things that start with DA that are available in my directory, and that's the data subdirectory. And it also automatically already lists the files in there. So if I navigate down and press enter, it will autocomplete the full path to the name. And actually autocompletion also works with functional variable names. If I type LO and press tab, R will suggest here all the R functions that start with LO. Okay? If I carry on A, come on, there was a longer list, and still here those start with LOA, and then tab, and it will autocomplete. All these keyboard shortcuts help us, saving keystrokes. Data, IPRG, enter. A function with its input and actually load automatically creates, automatically loads this new variable that is here, IPRG. And tomorrow we'll learn about these types of variables that are like spreadsheets, if you want, they're called data frames. And tomorrow we are going to look into details what these are. I'm going to create a new script here because I'm going to start with a new topic. Let me call it script 2.r. So, any questions so far? Let me. So this was the use of the new function load with its input. Okay, so we have learned about variables, and so far the variables that we have created were always of length 1, 10, 3.31, and so on. We can also create longer variables with a new function called C to concatenate or create, construct. C1, 4, 7, 3, 12 will take these individual variables, 1, 4, 7, and combine them, concatenate. As we have seen previously, instead of just printing them out, I can store this new variable into X or overwrite X if I already have it. if you look here in our global environment pane, we see that case X wants 4, 7, 3, 12. And we have this little kind of 1:5 that tells us that it has 5 elements, 1 to 5, and these are numbers. So all the variables all these type of variables, whether we have a certain length or a length greater than 1, in this case 5, or y, or what is the other one, b, all these variables are called vectors. And these vectors can have only one element, have a length 1. So for example, length of A, of A, for example, is 1. A only contains 10. But length of X is 5 because I have 5 elements inside this vector X. Now let me maybe overwrite Y, and in Y store 1 like this. Control L, X, Y. Length of X is 5, we have seen this. Length of Y is 1. But there is a big difference here between my Y and my X. My Y is quoted. So my X are numbers. So it's a vector, in this case of length 5. It's a vectors of numbers. And I can find this out with the function, parentheses, function X. Okay. Class of X is numeric, are numbers. The same thing with Y. Y is a character. So irrespective of what I have inside the quotes, whenever we have something that is quoted, it is a character. So like the function that we had before, load, and then we quote the name of the file that we want to load. Let me give you another example. Let me create a function called PEPs for peptides. And now I'm really going to embarrass myself. What I'm going to type are not real peptides, but I'm not going to waste time by actually typing real peptide sequences. But here we go to give you a kind of slightly more interesting example of a variable. So in this variable, let's assume that these are 3 sequences of peptides. Or this could be 3 sequences of DNA. DNA, it's easier to type for the alphabet. So, what is class of DNA? It's a character. What's my class of PEPs? It's also a character. How many DNA sequences do I have? I have 3. How many peptide sequences do I have? I also have 3. Oh, let me. So we have, yes? Sorry, right? So, the reason I'm putting this on different lines is to make it easier, to make it fit on the screen and easier to read, but R will not mind whether it's on one line or multiple lines. No, okay. So yes, these are three characters, and they are combined into one vector that has three elements. There would be another function called paste that I believe we'll see later that could take three kind of vectors of length 1 and combine them into one big one. But C concatenates its element to create a new vector. And actually, leading from your question, so what will I get? What will I get here? After executing these commands, let me call this DNA2. Good. So what is DNA2?
DNA plus this new string.
Yes. So DNA2 is a vector of numbers. What does it contain? Well, it contains what DNA contained plus an additional sequence at the end. So what was the length of DNA? I believe it was 3, and now the length of DNA2 will be 4. Okay, so I think I can use X. Okay, now this one is a little bit mean, a bit naughty. What happens if I do this? So what is X? A vector of numerics, exactly. What does C do? C takes vectors and concatenates them together. So C is supposed to concatenate a vector of numerics and this. What is quoted 100? A vector of characters, yes. So the big question is, what happens if I concatenate a vector of numerics and a vector of characters? White out? Or guess? All characters. Yes. And why is that? Do you have an idea? Sorry, you say. Fantastic. Yes. I can always convert a number to a character. Actually, I can convert anything to a character by quoting them. And in some occasions, I could convert a character to a number when what is quoted is actually a number. So characters are very generic. It's a very generic class, if you want, type of object, whereas numbers are much more specific. And so vectors can only hold one type. If my first element is a number, all the other elements are also numbers. If any number, any element has one type, I know that all the other elements of that vector will have the same type. And whatever the length of my vector. Okay? So we have seen numbers, we have seen characters. One that we haven't seen yet, but that we will see later on, are logicals. And logicals are either true or false. True, all spelled out in capitals, and false, all spelled out in capitals. So I can create false. This vector of logicals of length 3, where the first element is true, the second element is false, and the third element is false. And same thing, along the same line as before, if I try to concatenate true, false, false, and the character true, everything will be converted to characters. And so this is this is important because it allows us to reason on our data. If I have a vector, what is really important for me to know is what is stored, or what kind of data is stored in my vector. That's the first thing I need to know. And the second one is, what's the length of my vector? I don't need to know the actual values that are contained in the vector. R will figure it out, and R will do the calculations. But it's important for me to know what kind of vectors I have. Sorry, I missed and that comes back to questions that we had before with kind of big data that fit or don't fit in Excel. To some extent, if I have a vector of 2 elements or a vector of 10 million elements, I'm not going to, well, I could look at the vector of the values in the first and second place of my small vector. But really what matters is to know, well, what do I have in this vector? Do I have numbers? Do I have characters? Do I have logicals? And that will define what I can do with it, irrespective of its actual length. Let me take DNA2 that we created before, and I'm going to introduce a new type of funny character, which is the square bracket. Square bracket allows me to extract a specific element of my vector. Okay. This means extract the third element of DNA2, which is this one. So C allows me to grow my vector by adding elements at the end or at the beginning. Like this. So here I concatenate this new DNA sequence and whatever I have in DNA2. But I can go back and extract specific elements of my vectors using the square bracket operator. Now, my challenge to you is the following one. I would like to create the following vector. Let me write it here. I would like to create the following vector . Okay. Have you seen what I've done? This vector contains, in that order, element 3 and element 4 of DNA 2, followed by element 1 and element 2 of DNA 2. Yeah, do you understand? Because I realized that just showing this is not totally helpful. So let me add a comment here. Element 3, 4, 1, 2 of I'm going to add a comment here. Okay. So could you create a new variable that is this one, without, of course, copying and pasting, without typing everything one by one, but using what we have learned, which is the C function to concatenate and the square bracket operator to subset. And could you put your blue sticky notes up once you have created this new variable that we shall call DNA4? Yeah, sorry, of course you don't have variable DNA2 already. Okay, let's do the following then. Sorry about that. Let's create a variable altogether that we call, we'll keep it called DNA, and let's type the following. Letters. Letters is a built-in variable that contains all the letters in capital. Okay? Now I would like you to create the following variable, C, D, A, B. Create a variable, let's call it whatever you want, that contains in this order capital C, capital D, capital A, capital B, but without typing C, C for concatenate, C, D, A, B. Create this new variable using the letters, the built-in variable letters. Okay, I don't see any red sticky notes and many blue sticky notes. So there are different ways of solving that exercise. Anyone has a suggestion for me? Yes, please. Okay. So you created, for example, I 3, 4, 1, 2. Is that correct? Something like that. And then letters, square bracket operator for subsetting, and we want letter 3, 4, 1, 2. That's exactly what I contains. Yes. Yes?
Letters 3, open bracket 3, letters 4, letters 1, letters 2.
Okay. So we want to concatenate letters 3, letters 4. Is that?
Yeah.
What? Yeah. Letters. What was it? 1, 2. Yes. Another way would maybe be we start with 3, 4, 1, 2. So all these, yes? Absolutely. So here I create the temporary variable I that I use for subsetting, but you can also do like this. Absolutely. And these two are essentially the same, where here we create a temporary variable. Temporary variables are cheap, but sometimes it can be confusing to have many temporary variables in our global environment. But if this is too long of an expression, then you are very welcome to create temporary variables to kind of reduce the length of the expressions. Yes. And so maybe as an alternative to this, let me show you quickly another function. It's a special function that is the colon. Colon means create a sequence of integers from whatever we have on the left-hand side to whatever we have on the right-hand side. So for example, earlier today I typed 1:100. That creates the sequence from 1 to 100. And so here, instead of typing explicitly, oh, sorry. This should be C. Yeah. Instead of concatenating 3 and 4 and 1 and 2, I could create a sequence from 3 to 4 or the sequence from 1 to 2. Now, let me demonstrate you and that would be kind of the last big new concept in terms of R that we would see today. Let's create X and subset letters to, let's say, 1 to 5. 1 to 5. Okay? So that we have a relatively short vector as example. So we have seen that X square bracket operator to do the subsetting, and we have seen that we can use indices, numbers, to do the subsetting. But we can also use booleans to do the subsetting. So if I type false, true, I will not get the first element of X. I will get the second element of X. I will not get the third element of X. I will get the fourth element, and I will not get the fifth element. These two commands will produce the same output, B and D. But this one does the subsetting based on indices. This one does the subsetting based on booleans. And while this expression on line 32 looks annoying because it involves lots of typing, and of course in real life we would probably never start to manually type true, false, and so on. This command illustrates a very important concept in terms of data analysis and using R for data analysis. And to do that, let me create Y. Yes, let me create Y, but to to do that, I'm going to create a new. I'm going to use this new function called rnorm. And rnorm 10 draws 10 random numbers from a normal distribution. This is a normal distribution with mean 0 and standard deviation 1. So this is y. This is my y. If you run this command, you will get 10 other values. And if I rerun this, I get 10 other values. Okay, it's a random draw. Now, imagine I would like to only have those that are greater than 0. What could I do? And in R we can use greater than operator. So is 5 greater than 1? It's true. Is 5 greater than 10? That is false. So now what happens if I type y greater than 0? I will do this comparison 10 times. My first element of y, is it greater than 0? False. The second one, is it greater than 0? True. Third one, true. Fourth one, false, and so on. So if I do this, I will automatically create a vector of logicals whose a false corresponding to, or falseness corresponding to the positions where y was not greater than 0, and true for the positions where y was greater than 0. So let me store this in I. And so now here I have a vector of logicals that I can use to subset y. So while the example here looked a little bit convoluted, and indeed it is, in real life, I can't think of an example where I start to type true, false, as it is. However, these vectors of logicals is something that happens very, very often when we analyze the data. And these vector of logicals can themselves be used to subset other vectors. What is important in these 3-4 lines of code here? Is not to know exactly what values are stored in the y. But to run this, what I need to know is that y is a vector of numbers. Y was a vector of characters. This operation wouldn't make much sense. It doesn't mean that it would work in R, but it wouldn't make much sense. So when I run this, knowing that y is a vector of numbers of length 10, what is the output going to be? My input was a vector of numbers of length 10. The output of this command is a vector of logicals of length 10. And that kind of reason is essential because I do not see my data. I do not look at my data. I could, because it's very small, but I don't need to do that. Just as the example before, I can have a really, really big spreadsheet data set, thousands of rows and columns. To to do that kind of operation, I don't need to know exactly what's in there. I need to know some sort of property, dimensions, or in this case length. So I know that now in I have a vector of logicals of length 10, and I know that I can use I to subset Y, because they have compatible dimensions. And I know that every element in I that is true corresponds to an element of Y that is positive. And I can now run this, and without looking at the values, I can trust that this is the result I'm interested in, all the positive values of Y. And so, while what we have seen so far was basic syntax, was I think challenging because it's new syntax, it's a new piece of software, it's maybe a new way to interact with the software. This example here encapsulates, I think, an important property of data analysis. You don't need to see the data. You don't need to know what the data is. It's enough to know properties about the data. And then you can reason using these properties to calculate new values, new summaries of your data. And I really like these kind of examples because I think they exactly show what we need to know. Some properties, length, class, these attributes. Now there is another very special type in R which is called NA. NA for missing data. I will not talk too much now about it. Maybe I could give a quick example. So let's create first maybe x, values 1, 2, 3. Here it is x. And if I want to calculate the mean of x, I can use function mean. And there is function median, min, max, and so on. Now imagine I have x that contains 1, 2, missing value 3. If I now try to calculate the mean of x, I do not get 2, but I get missing value. Because this unique unknown in my element kind of screws up the whole calculation. I is not taking any risks, one missing value, one value that is not available, and the result is not available. So, my question to you is, how could I calculate the mean of this vector despite the fact that it has an A? And there would be many ways to do this. One would be to look at the documentation of an A. Second would be to use the square bracket approach to do the subset. Okay, I'll give you a couple of minutes to try to figure out one solution to calculate the mean of this vector. So could you take your sticky notes down, and once you have found a way to calculate the mean of 1, 2, missing value 3, could you please put your blue sticky note up again, or call us if you have a question. Okay, let's do that together. Any suggestion on how to solve this? Anyone? Yes? Exactly. So the easiest way here would be to look up the documentation of mean, question mark, mean, and realize that among the arguments, there is this one and a.rm. The default value is false. And it basically means, well, do not remove missing values before calculating a mean. But if we change it, first it will remove the missing value, and in this case there is only one. But that would even work if we had a vector of length 1 million and we only had 1, 2, 3 and then all the rest missing values. Doesn't matter. First we remove missing values and then calculate the mean. Another one would have been to say, well, calculate the mean of x and we want to have 1, 2 and 4. But of course that only works because it's small data and we can look into it. Another one would have been to say -3. Negative indices means remove these indices. That's something new, so you couldn't have figured this out. So x -3 means all the elements of x except the third one. And the last one that is interesting to know is an a.omit. An a.omit is a function, we have parentheses here, and it will return its input stripped of all the missing values. And then here we see there are some additional attributes that we can really ignore now. This is just kind of additional information that we can forget about. For now, you see it says that the third element used to be a missing value. So we could also say but clearly, I think the best solution in this case is to read the documentation of mean. So sometimes reading the documentation does help and figure out that this an a.rm equals true or false. And an a.rm is an argument that you will see over and over again for mean, median, max, min, and so on. Whenever you have a missing value, check the documentation and there might be an a.rm. Yes?
Is there a way say is not,
Yes. So is.na, which elements in X are NA? Is.na is a function that will return false if there is no NA, true if there is an NA. So how can we get the opposite? Change every false to true and every true to false. And we can do this using the exclamation mark. Exclamation mark is the negation. It will transform any true to false and false to true. And so we will stop here. It's 1:26, but there is a dinner, I think, at 6:30, so we cannot get over time. So for those that felt already confident with using the command line interface, interacting with R, I think it was a pretty easy. But for those who, this is completely new, believe me, this is, we have achieved a lot. Learning about variables, finding out that you can look at the documentation file of the function and use as a.rm, set it to true. The subsetting, the y subsetting by I. These are kind of already fundamental concepts that we will kind of carry on using and reusing and kind of exploring tomorrow, while we'll start to see more complex types of data, not only vectors. Okay? So thank you very much for today. I'll see you tomorrow. Do we start at 8? From 8 to 9 is optional, right?
So, 8 to 9, just want to continue the same kind of division as the sky jump
So 8 to 9 is what we will be doing. If you have questions, you guys want to ask. If you're down at 9, you won't get an extra time. Like, or for example, if you like to make customized your own data or some other. So we have a dinner at 6:30. Which is a very short walk from here. It's pretty much at the edge of the campus. So you just go on the Huntington Avenue where the green line goes. You just go towards downtown for 5 minutes. And the restaurant is called Uno and our reservation is 6:30.
One last thing, sticky notes are not over. Could you write one positive thing about this afternoon on your blue/green sticky note? And something negative or that needs improvement on the red sticky note. And could you put the red sticky notes on this side of the table and the blue sticky notes on this side of the table? It's anonymous, of course, but please provide feedback so that we can improve for next time. So just stick them there before leaving, please. Thank you very much.